Okay, so now we are going to look at what happens if you're doing a problem where you have this object on a ramp. Okay, so imagine we have a box sitting on a ramp, and let's say we want to see how fast is it going to slide down the ramp. Okay, so let's say you have a mass of 2.5 kilograms. Let's say the coefficient of friction between the surface and the block is 0.28. And I'm going to see how fast will it accelerate when you release it. Okay, so I need to think about what forces are acting on the box like normal. So I have gravity pulling down. Gravity always pulls straight towards the earth. Okay. Now my normal force on this one's a little tricky because the normal force is always perpendicular to the surface. So because my surface is tilted, my normal force is also going to be tilted. Okay. And then I'm going down the ramp. There's nothing pushing me down the ramp. Gravity is partly pushing me down the ramp. I'm not applying a force, so nothing's going to point down the ramp. But if I'm going down the ramp, friction points up the ramp. So your friction and your normal force are always perpendicular. The friction's always going to be parallel to the surface. Okay? So you have a couple options. Oh, by the way, my angle is a 37-degree angle. Okay, we'll need that in a second. Okay, so you have a couple options. You can do this problem where you just do your normal X and Y axis, but you're gonna have an acceleration in both directions, X and Y. So what you're gonna have to do is you're gonna have to find acceleration in the X direction, you're gonna have to find acceleration in the Y direction, and you're gonna have to make a triangle out of the answer. And two of these are also at an angle, so there's a ton of trig there. So we are going to eliminate a good chunk of the trig. So let me show you a little trick we do. So I usually did this with transparencies, but I don't have transparencies. So we're doing it this way. So here's our normal, typical XY axis, right? X is straight down, or X is straight to the side, Y is up and down. But watch what happens if I turn my entire axis like this. Okay, so see how now my FF is in the same direction as the X direction. My FN is in the same direction as the Y direction. All I have is one angle here. Also, I'm not accelerating this way at all. Okay, I'm not flying off of or sinking into the surface, which means I don't have any acceleration in that direction. So I only have acceleration in one direction down the ramp. So I've just eliminated all but one of my angles. Now it's a little tricky to kind of think about sometimes, but basically what we're going to do is we're going to draw your thing that's rotated. Now look at what's at an angle in this case. It's your FG. It feels weird that your FG is going to be at an angle, but it's just because we're rotating the whole thing. So the way I typically draw these, it's very helpful to sometimes draw them like this first. But then when we actually go to do like the free body diagram that I'm going to write my force equations from, it looks more like this. You rotate it, and we've eliminated almost all of our angles. We have one angle left. Now the other thing is it's kind of easy to mess up where you draw your angle. So essentially, think about what we did. So we started like this. We rotated it until it lined up with the ramp. We know how many degrees the ramp is from where it started, right? So that's how many degrees you rotated it to get to this. So what that means here is the angle is how many degrees you turned it from being straight down. Okay, So that's where that angle actually goes. Now what that means is when you're doing your sine and cosine, you need to think carefully about which one's going to be your sine and which one's going to be your cosine, because it's not what we've been doing. We've been measuring everything from the x-axis, not the y-axis. So sine is still opposite over hypotenuse, cosine is still adjacent over hypotenuse, okay? I also want to remind you of one thing from trig that you may or may not remember, and that is that sine over cosine equals tangent. That comes up sometimes in these problems, so I just want to throw that out there. Okay, so we're going to go back to our problem. So we are going to look at it like this. And so now we're going to write our force equations. Okay, so FG, not in the x or the y, it's in both. So our x equation is going to have FGX. Okay, and then we have FF pulling backwards, and that's going to equal MA. Now that is the acceleration that we're actually finding. It's the acceleration down the ramp. Okay, so then your other equation is going to be your vertical forces. So your Fn is going up, and then again your Fg is not going straight down, it's going at an angle, so it's going to be FGY equals MA in the y direction. Now the block is not moving this way, which means it's not moving this way, which means this is 0. What that tells you is that your Fn is going to equal your FGY. Okay, I'm going to show you a couple different ways to do these problems. I'm going to show you one where you kind of plug in numbers as you go, and then the second one I do, I'm going to do with just leaving the letters in all the way through, okay? So, I have a triangle here. You may want to go ahead and find your values for that before you go too far. So essentially, you have a triangle where this is 37 degrees, okay? This is FG, so FG is M times G. So this is gonna be mass times G. So your FGX is mg, and then your x is down here. That's opposite now. So that's going to be mg sine theta. And your FGY is going to be mg cosine theta, which again is flipped from what you're used to, but still true. So your FGX is going to be 2.5 times 9.8 times sine of 37, which is going to come out to 14.744 newtons. And your FGY is going to be 2.5 times 9.8 times cosine of 37, which is going to be 19.5666. Okay, now notice I wrote a lot of digits here. That's because there's several steps to this process. And so we don't want to round till the very end. Okay, now I found FGY, which means my normal force is equal to my 19.5666. Okay, so that's going to be important in a minute. So what we're ultimately looking for is this acceleration. So I'm going to take this equation, I'm going to write it here. So FGX, which I just found, minus, I am going to put my equation for FF. So that's going to be mu times normal force equals MAX. Now let's think about what I have. Okay, FGX I found, mu I have, Fn I did just find, because we know it's equal to this, and M I know. So I can go ahead and plug my numbers in here. So my acceleration is going to be FGX, which is 14.744, minus mu, which is 0.28, times Fn, which is equal to your FGY, which is 19.5666, over my mass of 2.5 kilograms. So I'm going to type that in. and I get 3.706, so 3.7 meters per second squared. Now again, gravity is what's accelerating this block. So if you end up with an answer that's bigger than 9.8 and there's nothing pushing it down the ramp, then you did something wrong, okay? So that's one. I'm going to show you one more to practice rotating and also show you what happens if you don't plug the numbers in early, okay? So, excuse me. Let's say I have a surface and I have a block and I want to know the coefficient of friction between the two. I want to see, I know the coefficient of friction. I want to see how high can I tilt it before it starts to slide, okay? So let's say I have this object. I am trying to determine the angle at which it's going to start sliding. Because if it's sitting still, sitting flat, it's not going to slide. As I tilt it up, at some point, you're going to hit a spot that it's going to start to slide down. Okay, you can do this at home. You can try it. So I want to know, when is it going to start sliding? So I'm looking for theta. So essentially what you're looking for is the maximum static friction force. What is the maximum static friction force? What you have to overcome to get it to slide, okay? So we're gonna basically find when all the things are balanced. So let's see, you need to know the coefficient of friction. Let's say the coefficient of friction is 0.52, okay? That is actually all you need to know to figure out the angle at which your object is going to slide. So let's see why. So here's your object on your ramp. You're going to be increasing the angle until it starts to slide. So we've got gravity pulling down. We've got normal force perpendicular to the ramp. We've got friction force pointing up the ramp. And that's it. There's nothing pushing down the ramp. So again, we're going to rotate it. So think, again, picture spinning it around so that instead of being like this, your axis is more like that. Because again, we can make X and Y whatever we want in order to make our problem easier. Just like we can make down negative, or we can make it positive, as long as we're consistent. So as long as everything we're doing is measured from those axes, we're good. So we're going to rotate the whole diagram. Okay, we have normal force, we have friction force, we have gravity, and again, it's measured from here, because that's how many degrees we had to tilt it to get it to here, okay? So, we're going to do two equations again. So in the x direction, we have FGX, we have FGX, and then pulling back, we have FF equals MAX. And then in the vertical direction, we have FN minus FGY equals MAY. Okay, now, if I'm trying to figure out when is it going to start sliding, I'm essentially trying to figure out when is the static friction force equal to the gravity, because if I go any steeper than that, then it's going to fall. So really what I want to do is see when both of these are balanced, when everything is balanced. Okay. And again, we're looking for the maximum angle, so this friction force is going to be the maximum friction force, which is going to be the mu times Fn. Okay, so this is going to give me one piece of information, and that is that Fn equals FGY. And let's think about our triangle again. So if this is our triangle, FG is the hypotenuse, which is mg, and the y component is this one here, which is the one that's touching it, so it's the adjacent, which is cosine. So we can write this as mg cosine theta. Okay, now hold that thought, we're gonna come back to that. So now we're gonna go up here. So we have FGX minus FF equals 0. So that tells us these two are equal. Okay. Well, we know that FGX is mg, and then x is the opposite this time. So it's going to be mg sine theta. Okay. So we also know that the friction force is mu times Fn. Okay, now neither of these seems super helpful in finding our theta, but let's keep going. Okay, so we know that this is equal to Fn. So I can take that and plug it in there. So mg sine theta equals mu times mg cosine theta. We're solving for theta again, remember? So we're trying to find what angle will it start sliding. I want you to take a second and look at that equation and think about how you're going to solve that for theta. Keep in mind what I told you earlier. So first of all, if I'm solving that for theta, I'm going to see that there's some stuff that's in both sides of the equation. Okay, so I have an mg here and I have an mg here. I can divide that over and it goes away. So we're left with sine theta equals mu cosine theta. Now I'm solving for theta. Okay, so all I need to do is get the thetas together and then I can solve. So I'm going to divide the cosine over. And I have mu equals, now what did I tell you sine over cosine was? Tangent. So guess what? I can just take this and I can do theta equals inverse tangent of mu. So I just have to do inverse tangent of 0.52, which is 27.47 degrees. So that means that I can go up to 27 degrees, but if I go to 28 degrees, it's going to start sliding. Okay? So that is my answer. So there are benefits to leaving letters in all the way through. Plus, then if you make a mistake early on, it doesn't carry through like it would if you were doing it that way. So that's ramps.